Okay, so this example now is card number 6. It's on page 45 in the workbook. And we're given this circuit here, and the resistors aren't labeled. And so sometimes that presents a bit of a problem. And so, you can label the resistors if you wish. You'll notice that when Mr. Chalk did the drawings or the redraws of it, he didn't bother to label the resistors with R1, R2, and so on, but he did label the junctions. And he's really big on putting a little black dot on each of the junctions, right? Where we would consider it to be a node. Now a junction, like this one down here is not really a node because current don't divide there. Anywhere where current divides or recombines, he puts a black dot on, and he's really big about that. And so, that's not really what shows a parallel connection. And so in circuits that you get from me, if I draw them, I'm not really big on the dots, right? And so you can't go by that alone with respect to what a parallel connection is. But you will notice that Mr. Chalk has labeled the nodes. And he has labeled, for an example, this dot, this dot, this dot, and this dot with 4 ends. And the reason for that is, look, everything connected all across here, right, is all at the same potential, because, everything connected to that is all at the same potential. And so that's a single node. And, if you read some textbooks and some literature, it talks about the drawing of circuits. Try to make sure that your resistors aren't on diagonals because that's confusing and so on. Well, the idea is that, look, different circuits can be drawn in different ways. And usually you draw it in such a way as that as simple as you can make it. And so this circuit is stretched out a bit, but all of these resistors, the 48, the other 48, the 12, the 30, the 45, the 282, and the 141, they're all connected to the same point. And so, yeah, that's junction or node in, no doubt about it. And so, then he's labeled this node here as P, this one here at the negative on the battery, because there's no current division taking place there. He didn't give that one a node. In multi-sim, that's the one you got a ground there. Put your ground in there. The negative on the battery is generally considered to be a ground, right? Okay, so we are asked to find the total resistance of the circuit. Find the current in the 45, that's the current through this one here. Find the current in the 12 ohm, of course that's this one. And find the voltage drop at 116 ohm. So a couple of things now. I usually likes to note on my circuit what I'm asked for. And so the current in the 45 ohm is this current here. The current in the 12 ohm is this one here. And the voltage drop across the 116 ohm is this one here. And so again, right, I like to note them because that helps you concentrate your calculations into coming up with the correct answers, because you don't have to calculate the voltage, current, and power for each individual device, just the ones that you're asked for. Okay, so the next thing then is that we want to more or less identify series and parallel relationships. Okay, so now we can look at this one and we can say, well, these 3 resistors here, they're in parallel. These two 120s right here are in parallel. And these two here, the 141 and the 282, are in parallel. So we could do all of them as the first step. Okay, so what I'm going to do now is, here is the first redraw that Mr. Chalk done. And so I'm going to take that diagram, I hope I am, and I'm going to copy that back onto the first page. Okay, so now up here is the original circuit, and this is the one now that So Mr. Chalk has indicated with his dashed line here that he's going to tackle these three resistors first. Okay, so you notice he called this M, node N, node O, node P, node R, right? So it's good to note that. In addition, again, right, the current through here we're asked to find, the current through here we are asked to find, and the voltage drop across to 116 we are asked to find. Okay, so 48 in parallel with 4 in parallel with 48. So, you know, you could do that with the reciprocal formula. 2 48s in parallel is 48 divided by 2, and that gives us 24. Okay, so then we got 12 in parallel with 24, which is 12 times 24 over 12 plus 24, which is 36. And if we do that calculation, we got 8 ohms. Now, Mr. Chalk hasn't put any of the values on this circuit down here, but that means that this one here basically is 8. Now, okay, so on these redrawn circuits, the current through the 12 ohm, we got to come all the way back to the original circuit for that, because that one's gone now. But this current here through the 45 is still on this circuit, and the voltage drop across to 116, and so we don't have to go back to the original circuit to answer those two parts of the question. Okay, so he calls that RM in. Now, that's a little bit different from the way Mr. Matcham did his examples, because he would have called that RA. Okay, so now your own subscripts or labels that you put on these simplified resistances is arbitrary, and so that's completely up to yourself. Okay, so next he says that he's going to tackle these two resistors here in parallel, and that is the 141 and the 182. I'm sorry, the 282. And so he got his calculation here, 141 in parallel with 282. And so again now, you can do product over sum on those, and if you do that, you should come up with 94. And so again, the reciprocal formula or product over sum, whichever works, 94. And so that is this resistor right here. Now on this redrawn circuit, remember this here is still the current through the 45, and this is the voltage drop across to 116. And so I like to remind ourselves that we don't need to go up to these more complicated circuits to do that. So he has again put his 94 in, and now he's going to tackle this one. And so the reality of it is, as you're doing this on a test to save time and so on, if you can identify from the original circuit those three parallel combinations, I would do all those calculations before I redrew, just to save a bit of time. Okay, so these two resistors now here between R and P, they're both 120. So 120 in parallel with 120 is 120 divided by 2, and that is 60 ohms. So we can redraw and replace that by 60. And when we redraw, the current through the 45 and the voltage drop across 116 is still going to be part of our circuit. And so, we have to come back to this original circuit, maybe only for that current through the 12 ohm there. Okay, so now I think I should be able to pull in the next drawing that Mr. Chalk has included there on page 47 of the workbook. And okay, so this one here was the 60. This one, remember, was 8 that we calculated, and this one here, what value did we have for that? That was the 94 that we calculated. Okay, now the current through the 45 is still a quantity we want to know. Voltage drop across the 116 is still a quantity we want to know. Okay, so again now, if you're looking at this circuit here, you know, these two are in series, these two are in series. You could do both of those calculations before you redrew. He just tackled the 94 in series with the 116. So this here was 94 in series with the 116, and we should have, I guess, 210 for that, right? Okay, so then that was 210 here, just a linear sum of those. And so now the 210 here means that the voltage across the 116 is no longer part of our circuit, but the current through the 45 still is. Okay, so now he's going to tackle two of these here in series, and that was 45, the top one, in series with this one here, which was 60. And so 60 in series with 45, the linear sum means 105. So now our circuit is, this one was 8, we did that calculation. This one here is 105, we did that calculation. This one here is 210, we did that calculation. Now, remember that the current that flows in this branch here from end to end through those two resistors is still the current that flows through this 105. So this current right here is still the current through the 45 that we want. Okay, now I guess from the original circuit this one was 30, and so now he's telling you that we got 3 of these in parallel to think of. So we got 30 in parallel with 105 and 210, and so now that calculation, you know, I would say is equal to, maybe the easiest way to do that now is to say 30 to the -1 plus 105 to the -1 plus 210 to the -1. And so now that gets into our reciprocal formula, R to the -1. And if we do that, those 3 resistors in parallel are giving us 21 ohms. So this one was now 21, this one is 8, and this one here from the original circuit was 11. So RT now is 11 in series with 21 in series with 8, and the linear sum of those gives us 40 ohms, and that is RT, which was the answer to part A. So now, any questions or comments on that so far? So, in keeping now with our procedure of drawing our circuits on the left-hand side of the page, doing our calculations on the right, then our next trick is to say that down here, IT now is VT. Yeah, and he didn't label VT, but not that that matters. Divided by RT equals 120 volts divided by the total resistance of the circuit, which is 40 ohms, and that is 3 amps. And so remember now that, you know, the reason why we got to go through all this is that this circuit starts off with 2 resistors, an 8 ohm and 11 ohm in series with the source, and a bunch of other resistors connected on the road side. And none of those resistors got 120 volts across them. And so we can't apply Ohm's law to anything until we find the total resistance. And then we can apply Ohm's law to the circuit, which is what we did to calculate IT. Now, I wrote down 30 amps, 3.0 I'm trying to say there, I think, right? And that is now the answer to part B. Okay, so the idea now is that in our redrawn circuits, and so Mr. Chalk hasn't shown the source over here, but in our redrawn circuits, we have right here going through that circuit now, we have 3 amps. And so we can calculate the voltage drop across the 8 ohm resistor, the voltage drop across the 11 ohm resistor, the voltage drop across the 21 ohm resistance. And the idea is that voltage drop across the 21 we can bring up here as a voltage drop across the 30, the voltage drop across the 105, and the voltage drop across the 210. Why? Because the V21 here is the voltage drop between N and P, and that is the voltage drop between those two nodes or junctions. And so it is across all of the equivalent resistances that we combined in parallel to make the 21. Okay, so basically what we want to do now then is say that our next calculation, if we're moving up the page, is to say that the voltage drop across that 21 ohm, and I just call that V21. Now, Mr. Chalk, I think, has labeled that resistance as, I don't know if he labeled it at all, did he? He probably called it RNP because that was the nodes that he labeled there. And so, you know, V21 is the V across the 21 ohm. And so there's no other 21 ohm resistance in this circuit, and so that's good, right? Okay, so then that's going to be equal to the current that goes through there multiplied by the equivalent resistance that we had. And because of this series circuit here, the current through the 21 is IT. And so we have then 3 amps multiplied by 21 ohms. And that gives us 63 volts for V21. Okay, so that means that if I goes over here, this voltage right here is 63 volts. Now I could find the voltage drop across the 8 ohm, voltage drop across the 11 ohm as well, right? And so one of the things that you'll find is that this voltage drop across the 8 ohm, we're going to need that later when we gets up. But I'm going to calculate it later because we know that IT goes through there, right? Because IT is going through that 8 ohms, and we'll calculate that a bit later, but we do need that value. The voltage across the 11 ohm is not helping us find the answers to the circuit, and so we will now say that if this voltage is 63 volts, then the voltage between N and P is 63, right? And so we need to know this part right here is 63 volts. We can move up to the next circuit. The voltage between N and P is indeed 63 volts. Now in this circuit right here, the voltage drop that we're looking for is this one, and we can use voltage division now. It is a piece of that 63, that voltage there. In addition to that, the voltage between N and P is 63, so we can find this current right here. Okay, so we still have up here VNP, let's say, is 63 volts. Okay, and so I guess we can say here V Now, what that means then, see, is the current that we're looking for through the 45 is this current right here, right? And so the current through the 45 then will be VNP divided by the resistance of that branch, and the resistance of that branch was this 105. So 105 ohms. And let me indicate that we're moving up now, doing our calculations across there. And so that voltage now is 63 volts divided by 100. Oh, I'm sorry, that current 63 volts divided by 105 ohms. And that gives us 0.6 amps, or 600 milliamps if you would, and that is the I-45, which was the answer to part B. Okay, so I made a bit of a mistake down there when I thought we were asked for total current for part B, which I guess we usually are. And so just let me erase that down there. So in addition to that, the voltage drop here across this 116 ohm was something that we wanted to know, right? And so I guess we'll move up and do the calculation up there. But remember now that what we want to say is that the current through the 116 ohm is equal to VNP divided by the resistance in that branch. And the resistance in that branch was that 210, right? Because we still got the 63 volts across the 210, and that's going to give us this current, which flows through the 44 and the 116. I'm sorry, the 94 and the 116. So that is over here 210 ohms. And so the current in that branch, we have 63 volts over 210 ohms. And so similar calculation to this one down here, the resistance is twice as big. It means the current's going to be half as much, right? 0.3 amps. And so that means that, in this circuit here, if I calculate 0.3 in that branch, then that means up here, I got 0.3 in that branch. Right here, of course, we can bring that information up to all of our parts of circuits. And so for part C, part D, the voltage drop of the 116 now, if I got the current through it, right, then the voltage drop across the 116 is equal to the current through the 116 times R, of course. And we have 0.3 amps for that, multiplied by the 116 ohms. And so the voltage drop across the 116 ohm will be equal to, if you work that out, it comes out to 34.8 volts. Okay, so now that is the answer to part D, and very often you don't do them in order, and that's no big issue. Okay, so now remember that we calculated 3 amps through this branch right here, that 8 ohms, and so we're going to move up now to our original circuit. And whether you look at this circuit or the original one up there, what we want to say now is that, look, you know, that this 8 ohms right here, right, and we want the voltage drop across there. Okay, so basically we can say that the voltage drop across that 8 ohms is equal to I times R, and IT goes through there, and of course it is 8 ohms. So that gives us 3 amps times the 8 ohms, and so that V8, let's say, is equal to 24 volts, and that is across that branch. So that means that in our original circuit, the voltage drop across that branch between M and N is 24 volts, and so that is VMN, if you want to call it that. But it is indeed the voltage drop across the 12 ohm resistor. So that means that the last part of our question can be answered by saying that the current through the 12 ohm resistor is equal to VMN, if we call it that, divided by R, which of course is the 12 ohms, and we have 24 volts divided by 12 ohms, and that is 2 amps, and that is the last part of the question, equals, and again, 12 we can call it, right? Now, so when we think about that, that is the answer to part C. Now, so you notice then that on page 48, Mr. Chalk shows the original circuit. I think we got all the arrows here for his currents and so on. And he leaves you with a VIR chart. Now, we never really filled up much of the VIR chart, right? But we did put in certain parts of it. And we don't need to fill up the whole VIR chart, right? We calculated the current here, which is also then the current through well, see, you know, that current divides into these two. We calculated some voltages, but we certainly didn't calculate all the numbers for the VIR chart. Now, what we did was we concentrated on answering the questions. Okay, so let's think about this 2 amps now, back to that for just a second before I stops on this one. Here, between M and N, 3 amps flows through there. It's IT. That divides that point M into 3 currents such that it comes out here again as 3 amps, IT. And we said that 2 amps went through the 12 ohm resistor. So these two here are equal. That means that, you know, by current division, we should have 0.5 up there and 0.5 through this one. And Kirchhoff's current law then tells us 2 plus 0.5 plus 0.5 gives us 3 amps, which is the total current that goes in there, and the total current that comes out of there. And so remember now that the 24 volts across there, 24 over 48 confirms that calculation, right? And so the 3 amps divides into 3 currents, recombines into 3 amps. This 3 amps now divides into a current goes that way, current goes that way. I don't know if we calculated either one of them, but we calculated this one, and they adds up to this one. And so Kirchhoff's current law, Kirchhoff's voltage law, you know, applies across all that. You'll see that my solution to the problem all concentrated all on Ohm's law, but whatever rules you have, you should use to kind of find the solution to the problem. Concentrate your calculations on the specific questions that you've been asked for.